Welcome back to the second video for Tech 240 on Wednesday, February 17th. In the previous video, we talked about and we drew magnetic fields around a bar magnet and around an electromagnet. In this video, we're going to talk more about electromagnetism and how we can use electricity to create a magnetic field. It turns out that anytime you have current flowing through a conductor, you get a magnetic field around that conductor. We'll talk more about that and the shape of those magnetic fields in just a little bit. But first, I want to mention an extra credit opportunity. This is an extra credit opportunity that I usually give in Tech 240. For the past couple of semesters, I've been giving this opportunity, and I think it's pretty cool. It is an opportunity for you to get some extra credit by building a DC motor, by building and testing your own DC motor. And I will give you some parts that you can use to build this DC motor if you want. You can use your own parts as well, or you can supplement with your own parts. But I will give you, if you're interested, I will give you some parts. I'll show you them right now. So I'll give you a wooden block that might be useful as a base for your DC motor. I'll give you some pieces of angle aluminum. It's not really angle iron, it's aluminum. It's conductive, and this might be useful as maybe some support brackets or something. I'll give you a couple of screws. Here are some screws that you might need to hold things together. I will give you a permanent magnet. This is called a ceramic magnet, and it's moderately powerful. It's certainly powerful enough to make a DC motor. And I will also give you a bunch of wire. This is the wire from the last video. It's all wrapped up into a coil. I'm not going to give you it already wrapped up into a coil. You can wrap it up into whatever size and shape of coil you want to. I'll just give you a long length of wire, probably 7 or 8 feet of magnet wire, which is more than enough to make a DC motor. Yeah, you could probably make a DC motor with probably 3 or 4 feet of magnet wire, but I'll give you plenty of wire. Wire's cheap, so I'll give you plenty of wire to make a DC motor. One more thing, I actually don't have it right in front of me, but you will need to use sandpaper or something to scrape off the insulation on this wire because it's coated with a thin layer of insulation, so you will need to use something to scrape off that, that insulation around the wire. All right, so I will give you these components if you're interested. Just let me know if you are interested in building and testing a DC motor. And what I'll probably do is put these parts in a little baggie, and I'll probably just like tape it outside my door. So you can come by and pick up the parts for the DC motor anytime you want to that's convenient for you. Kind of like curbside pickup for DC motor parts. What I want you to do if you decide to do this extra credit, you need to design your DC motor, and then it needs to run for 30 seconds independently. Now, to get it started running, you can give it a little shove or a little flick to get it started running, but then once it's running, it needs to run for 30 seconds independently without you interfering with it or helping it once it's started. The power supply, I'm not giving you a power supply with this, but you can use some batteries at home. I will let you use up to 3 volts for a power supply. And that's pretty easy because you can use pretty much any standard battery like a AA or a AAA or C cell or D cell. 2 of those in series are going to give you real close to about 3 volts because each one is about 1.5 volts. Regardless of whether it's a AA, AAA, C cell, D cell, all those are about 1.5 volts. So if you want to, you can put 2 of them in series to get 3 volts. Honestly, you can run it off of just 1 too. That probably will work almost as well. So you can just use a single AA battery or whatever you've got handy. Not a 9-volt battery. That's obviously a significantly higher voltage. So you can use a single battery or 2 cells in series, or if you want to, you can come into Turner Hall. We have a whole bunch of power supplies in room 160B that you could use to run this thing. Just set it to 3 volts, and that's fine as well. When you are ready to test this, just take a video. You can probably just use your phone and take a video of this thing running independently for 30 seconds. And then send me that video. If it's too large of a file to email to me, then put it on Dropbox or Google Drive or post it on YouTube, something like that, and send me the link or send me the file to show me that your motor is running independently for 30 seconds. The extra credit I will give you is worth 1 lab assignment. So if you successfully build a permanent magnet DC motor, like this one, the parts from here, then I will give you the equivalent of 1 lab assignment's worth of extra credit. So you could end up with, how many lab assignments are there? I think there are 20. You could end up with 21 out of 20, potentially, for your lab assignment score. It gets better than that, though, because there are several different kinds of DC motors. I would recommend starting with the permanent magnet DC motor that obviously uses a permanent magnet like this one that I will give you. If you successfully test this one and it works, then you can build a different kind of DC motor. We'll talk about some different kinds. There's also a series wound DC motor and there's a shunt wound DC motor. So those are another 2 kinds of DC motors that you can build and test, and I'll give you even more extra credit for that. So it's possible actually to get 23 out of 20. I've never had any student build all 3 types of DC motors, but I have had students build 2 types of DC motors. So it's not impossible. It's not easy. I don't want to tell you that it's simple or easy, but it's been done and it can be done. You just have to be kind of careful and patient and try a bunch of different things out to get this thing to operate correctly. The easiest is definitely the permanent magnet motor, so that's why I recommend starting with that. All right. Like I said, you can supplement with your own parts. If you don't want to use my parts at all, that's fine. You can get your own parts. You can add your own parts. The only thing I don't want you to do is to go online and buy a DC motor kit, because they're out there, you can buy them, but I don't want you to, because I want you to do a little bit of research on your own, do some trial and error, and figure out how to make this thing operate. That's part of the learning process. So I don't want you to buy a DC motor kit. I've seen those, so I know what they look like, so I'll know. So if you're interested in building a DC motor, let me know, shoot me an email, or tell me after one of our synchronous class sessions, and let me know when you want to pick up the parts, and I'll set them out for you, and we'll get you these parts for the DC motor. Now back to the original material. What we're going to talk about in this video is electromagnetism, and specifically we're going to talk about how we can create a magnetic field with electricity, by sending electricity or current through a wire. We already saw that we could do that. I mean, we have evidence of that already in the first video today, where we mapped out the magnetic field around that coil of wire that had current going through it. So we know it exists. We know there's a magnetic field around there. We saw that there's a magnetic field around that electromagnet, but we want to talk a little bit in more detail about how it exists and how we know what the magnetic field looks like. All right, so this topic actually begins with a guy named Michael Faraday. You may have heard that name before. He's a pretty famous scientist. He was an English scientist in the early to mid 1800s. He didn't have a lot of formal education, which is kind of typical of a lot of the inventors and scientists of that era. But he's kind of known as the father of electromagnetism, because he did a lot of work in developing this field of science and even developing the first prototypical generator. So really the stuff that we talk about, not just in this video, but in the next class session, the early part of the development of the generator is really due to Michael Faraday. So he was an impressive guy, and he did a lot of work that led to our understanding of electricity and electromagnetism today. So this began, the legend says. There's always a bit of ambiguity with these types of legends, like how true this is, but it's a good place to start. The legend is that Michael Faraday noticed that when he had two wires suspended, like from the ceiling, imagine two wires suspended from the ceiling, and he noticed that when there was current flowing through those two wires in the same direction, so current is flowing down through these wires, or current's flowing up, either way. If current is flowing the same direction through these wires, he noticed that these wires tended to attract. They tended to bend toward each other and try to pull together. Conversely, he noticed that if current was going in opposite directions through these wires, he noticed that the wires would tend to repel or push apart from one another and try to increase their separation distance. And so that was his first indication that something was going on that he couldn't see. And that eventually led to his development of the field of electromagnetism. All right. So because of that experiment, Michael Faraday developed a convention for the magnetic field. So he determined there was a magnetic field around these wires, and he was correct in that. And he determined the convention of which direction we say the magnetic field is coming from and which way it's coming to. Remember how we said the magnetic field always goes from North Pole to South Pole? Well, that's largely because of the work of Michael Faraday. And he determined that when you send current through a wire, what happens is you get a magnetic field around that wire. And you can actually measure that. You can actually measure that, and you can prove that it's true. You get a magnetic field around a wire anytime you have current flowing through that wire. And what Michael Faraday also did is to define what the polarity of that magnetic field around that wire is. And the way that we remember that today is through a hand rule. I won't call it a thumb rule, but it's kind of a hand rule. And that is called the right hand rule for current carrying conductors. And I'll write this down in just a minute, but I want to show you with my hands first. You can see a little better in this view. So the right hand rule for current carrying conductors says that, let's imagine this is a wire, all right? And I've got current going in this direction through this wire, all right? If I want to determine the shape or the direction of the magnetic field that's around this wire, what I need to do is use the right-hand rule for current carrying conductors. So obviously use your right hand. So I've got my right hand. And what you do is you put your thumb of your right hand in the direction that current is going. So I'm putting my thumb along the direction of the wire in the direction that current is going. And then with the rest of your hand, you wrap your fingers around the wire. And that's the direction that the magnetic field is going. So this is a little bit counterintuitive, but around a current carrying conductor, you actually get a magnetic field that's going around in a circle around the conductor. And the direction is given by your fingers of your right hand wrapping around the conductor as your thumb is pointing in the direction of current. All right, so I could flip this around. If current was going in the other direction, now I'd have to flip my hand around. Now current is going this way, so I put my thumb going that way. And then once again, I wrap my fingers around the conductor. And now current is going this way. And actually the magnetic field is going in the opposite direction. All right, try that out a few times. Look at what happens when you have your thumb going this way, the field's going this way, and now try it the other way and see what happens, and you'll notice that it's going the other direction. All right, so try that out a few times and you'll see that the magnetic field is going in opposite directions as the current is going in opposite directions. So it kind of makes sense that if we have two wires that have current going in the same direction, that they're going to attract, and if they're going in the opposite directions, they're going to repel. Let's go ahead and write that down on a piece of paper so that we can remember that. All right, so the way we can say this is the direction of the magnetic field, which is B. Remember, I'm going to put that in there just to remind us that the magnetic field is given by the variable B. The direction of magnetic field, B, around a current carrying conductor, like a piece of wire with current going through it, but it could be any conductor. It could be a coat hanger with current going through it. Direction of magnetic field B around a current carrying conductor is given by the, I'm going to abbreviate this, right-hand rule, RHR, right-hand rule for current carrying conductors. All right. So it's important to note that this is the right-hand rule for current carrying conductors. Over the next couple of weeks, we're actually going to have a couple of hand rules. We're going to have 2 right-hand rules, and we're going to have 1 left-hand rule. But don't worry, for today, this is the only hand rule we have. So make sure this gets ingrained in your memory today, so when we add to it in the coming sessions, it won't be confusing. So the right-hand rule for current carrying conductors says that your thumb is in the direction of current flow, right? And this is normal conventional current flow. Don't be confused, but remember that electrons actually flow in the opposite direction. But don't worry about that. We're just concerned with the direction of conventional current flow, the way we always say that current is flowing, all right? So your thumb is pointed in the direction of current flow, and the rest of your fingers curled around the conductor give the direction of the magnetic field. Give the direction of the magnetic field B. Okay, so let's draw a couple of examples. I want you to get comfortable and familiar with drawing these examples. So let's say we have a conductor, and let's say I've got current going in this direction in that wire. And let's do another one. Let's do this wire over here. And in this wire, I have current going in the opposite direction. All right. So let's draw the magnetic fields around both of those conductors. I'm going to use a different color to show the magnetic field. So here's our first one. I got to put my thumb in the direction of current flow, so that's to the left. And then my fingers are going to curl around that conductor. If it helps, like, take your pencil or your pen and do this, and now you can more easily see that your fingers are curling around down behind the wire and then up in front of the wire. So the way that we draw this is to show that the magnetic field is going down behind the wire and then up in front of the wire. And then it'll curl around and go down again behind the wire. So down behind the wire, up in front of the wire, and down again. All right, so that's how you would draw the magnetic field to show that the current is going from left to right, and the magnetic field is going down behind the wire and then up in front of the wire. You know what I mean by that? By the magnetic field is going down, I'm trying to show that right now, down behind the wire and then curling around to go up in front of the wire, all right? Kind of like this. It's going down behind the wire and curling up in front of the wire. All right, so that's the way you can draw that. You can draw it just like that. I will note, I don't want to confuse anybody, but I will note that there's actually another way to show that. You can draw that another way. So this is kind of like, I look at this like, this is kind of from the left side perspective, but you actually could draw the exact same thing like this. This is also showing that the magnetic field is going down behind the wire, up in front of the wire, and down again. So these all show the same thing. These are all showing that the magnetic field is going down behind the wire, up in front of the wire, and then down again. All right, so that's the current going left to right. How about this one? The current going right to left. So my thumb needs to be going in the direction of current flow, and then my fingers are going to wrap around. So now they're going up behind the wire, and they're going to go down in front of the wire. Up behind the wire, down in front of the wire. All right, so they need to go up behind the wire, and then down in front, and then up and back again. Up behind the wire, down in front, and then up behind again. All right, so once again, this is kind of like looking at it from a left side perspective, kind of, but you can do the exact same thing by going like this. This shows the exact same thing. So it's going up behind the wire, down in front of the wire, and then up and back again. So once again, these are all showing the same thing, and these are all showing the same thing. But notice these are different. These arrows look different than these arrows, right? All right, so that takes a little bit of getting used to. You might need to stare at that for a little while and convince yourself that that makes sense. But just think about, I think it really helps to have your pencil or your pen in your hand and then literally put your thumb on the pencil or the pen and then wrap your fingers around, or do it the other way from left to right and wrap your fingers around, and you'll see how the magnetic field is going either down and back and up in front, or up and back and down in front. All right, so this is important and it's useful, but not really by itself, So what we do to make much stronger and more useful magnetic fields is, we saw this in the first video, we coil the wire. So we don't just have a wire, we have a coil. We put a coil in that wire, and for simplicity's sake, I'm only drawing one coil here, but of course in reality we have hundreds, maybe even thousands of we call it turns in that single coil of wire. And now what I want to show is what happens when we coil that wire. Well, first of all, let's say that we've got current through this wire going from left to right. All right, so current is going this way through the wire. All right, doesn't really matter, but that's what we're going to assume for right now. So let's draw the magnetic field. First of all, let's just think about the magnetic field in this section. So not even in the loop yet, not even in this loop, but just in this section. So it's going to look like this because the current is going from left to right. So once again, take your thumb, point it to the right, wrap your fingers around. So your fingers are going up behind the wire and then down in front of the wire. So they're going up behind the wire, down in front of the wire. Kind of like that. Okay, so that's the first part. You got to make sure you understand that. But then think about what's going to happen as I apply the right-hand rule around this loop. All right, so it's hard for me to show this kind of on this camera, but I'm applying the right-hand rule at every point in this wire, even as I go around the loop. All right, so I'm applying this at every point in the wire, even as I go around this loop. So I think it helps if you actually do this. Actually get your right hand out and pretend like you're going around a loop with your right hand. And what you'll see is that as you're going around the loop, your fingers are pointing up through the middle of this loop. No matter where you are on that loop, as you're going around it, see my fingers are pointing up through the middle of that loop. No matter if I'm over here, or over here, over here, or over here. My fingers are always pointing up through the middle of that loop, and then they would go down around the outside of that loop at every point in that loop. So if I drew the magnetic field around there, the magnetic field is always coming up through the middle of this loop of wire and down around the outside. All right, so that's what happens when we coil the wire. And what's kind of interesting is that if I had coiled it in the opposite direction, I would get the opposite effect. Instead of the magnetic field coming up through the middle and down around the outside, it would actually go down through the middle and up around the outside. You can try that and experiment with that yourself. All right, so that is what's going to get us a lot more useful magnetic field. And in fact, in real electromagnets, we have a lot more turns of that wire. So let's draw a slightly more realistic electromagnet. First, I'm just going to draw a cylinder. This is just a metal cylinder around which I'm going to wrap a coil of wire. Okay, so that is my metal cylinder. And now I'm going to connect a wire, and I have to be careful about how I'm going to draw this. So this is the way I'm going to draw it. So I'm going to draw it like this. And then we'll go out from there. All right, so here is our coil of wire. So now, instead of just one turn or one coil in that wire loop, we have how many? We have 1, 2, 3, 4, 5, 6. So this is slightly more realistic. Of course, in the real world, electromagnets have hundreds to, like I said, maybe thousands of turns. All right, so the current, let's just draw arrows for the current, okay, to make things clear. So the current's going from positive to negative. So the current's going this direction, like this, and it's going behind, and then it's going up like that. And so our current is going this way through the circuit, right? All right, that's just for to help us out as we think about the magnetic field. Okay, now we're going to apply the right-hand rule. And first, just to help us out, let's apply it right here, okay? And then we'll think about the actual coil of wire. So if I just apply it right here, current is going from left to right, so my thumb goes to the right, and then I'm going to wrap my fingers around, so it's going up behind the wire, and then down in front of the wire. So it goes up behind the wire, and then down in front of the wire. All right, so I don't really need you to draw these. If you're drawing the magnetic field around an electromagnet, you don't really need to draw these arrows on the wire leading to the electromagnet. This is just to kind of help us for now, okay? All right, so now we're going to apply the right-hand rule to all the segments of wire that are wrapped around this cylinder, all right? So think about applying the right-hand rule to all the segments of wire that are wrapped around this coil, all right? And you'll see that as you physically do this, I think it helps if you physically do this. Rotate your right hand around, and you'll see that as I'm doing this, my fingers are always coming up through the middle of the coil and then would wrap around the outside. So every single segment, at every single point in this coil of wire, my fingers are always coming up through the middle of the coil, up through the middle of the coil, and then they would wrap around to the outside. And what happens is when I wrap this around in a coil, and I have a bunch of turns of wire in this coil, all those little fragments of magnetic field, they all add together. They all add together. And so what I end up with is a considerably more powerful magnetic field that's coming up through the middle. And so we draw it like this. It's coming up through the middle, and then it's going down around the outside. All right, and we can draw a couple more of these lines of magnetic flux. All right, so that's what it looks like. All right. So we have our lines of magnetic flux, and now we can actually say which is the North Pole and which is the South Pole. Remember in the lab that we did, we couldn't say that because we hadn't talked about this yet. But now we have our convention that lines of magnetic flux always go from the North Pole to the South Pole. And we have these arrows here showing these lines are going from this side to this side. So if the lines always go from north to south, and these lines are going from here to here, then this side must be the North Pole, and this side must be the South Pole of this electromagnet. All right, now think about what's kind of interesting. I don't think I'm going to draw this, but I'm going to leave this to you to play around with. What would happen if I reversed the polarity of this voltage source? If I flipped it so that the positive side was up here and the negative side was down here, what would happen? Well, my current would be reversed. So now my current would be going the opposite direction. And if my current's going the opposite direction, then my magnetic field goes the opposite direction. So if I flip the polarity of the applied voltage, then I would flip the polarity of the resulting magnetic field. And the North Pole would be down here and the South Pole would be up here. All right. What's also kind of interesting is what would happen if I changed the direction that I wound the coil around this cylinder. All right, so it's kind of hard to draw and kind of think of, but if you look at, say, a top view, say this is the top. Let's look at a top view. So the way I wound this wire, the way I have drawn it wound, is kind of clockwise. All right, if I'm looking at it from this side, I would say it's wound kind of clockwise. Well, if I wound it the other direction, counterclockwise, if I had wound it the other direction, then what would happen is I would also get a reversal of the magnetic field. Because now instead of the magnetic field going up through the middle of the core and down around the outside, it would be the opposite. It would go down through the middle and up around the outside. Okay. All right, so those are two ways to change the polarity of the magnetic field. I could either flip the polarity of the applied voltage, or I could change the direction that I wind the coil. For example, instead of clockwise, I could wind it counterclockwise. All right, so those are two ways to change the polarity of the magnetic field. But what I want to talk about here is how to change the strength of the magnetic field. How to change the strength of the magnetic field of an electromagnet, like we've drawn here. All right, and it turns out there are actually 3 different ways. 2 of them are fairly obvious, and 1 is not very obvious. I would have you guess if we were in person, but the first one that's pretty straightforward is to change in, which is the number of turns or coils wrapped around here, all right? We're going to call them turns, and in the future I'm just going to call them number of turns of wire. And that's going to be abbreviated with capital N. In the number of turns in the coil. Because this magnetic field in green is simply the result of the summation of all of the individual magnetic fields resulting from each little segment of wire, each little turn wrapped around here, right? So if I just have more turns in this coil, I'm going to add more little pieces of that magnetic field together, and it's going to result in a stronger magnetic field. So I can increase the strength of the magnetic field by increasing the number of turns of wire in the coil. The second way is also pretty obvious. What I can do is I can change the amount of current flowing through this coil. And I think it's fairly intuitive to say that if I increase the amount of current, then I would get a stronger magnetic field. And that turns out to be true. You have a larger right-hand rule effect, if you will, if you want to think about it that way. So I have a stronger right-hand rule effect, and if I have more current, then I have a larger magnetic field. All right, so you can do that by increasing the voltage here. But I want to emphasize here, the voltage that's applied to the coil is not directly responsible for the magnetic field. It's actually the current that's going through the wire that is responsible for the magnetic field. Okay. The third thing is not quite as intuitive, but it is called, well, it's something about the core material, all right? So this core material turns out to have an effect on the strength of the overall magnetic field. And if you change it, what you could change about the core material is something called its magnetic permeability. If you've heard that word before, permeability, that means how easily does something allow something to pass through it, all right, in general terms. So what magnetic permeability is how well does it pass a magnetic field? If it has a high magnetic permeability, like say iron has one of the highest magnetic permeabilities, then it's going to result in a stronger overall magnetic field than if you had a core of, say, air. I mean, it could just be air. Your cylinder here could just be kind of a fictitious cylinder. It's just made of air. And that would result in a weaker magnetic field. Magnetic permeability of core material. All right. For example, iron is the best example is iron. Iron has a high magnetic permeability. And most other metals and pretty much all gases have a lower than iron, a lower magnetic permeability. But it's fair to say that in general, a metal would have a higher magnetic permeability than a gas in most cases. All right, so it's the ability to conduct magnetism. All right, think of it that way. All right, so if I want a stronger magnetic field around my electromagnet, I could have more turns of wire in the coil, I could send more current through the coil, or I could use a core material that has a higher magnetic permeability. All right, so what we can see here, I hope that you can kind of see this, there is a relationship between electricity and magnetism, because here we were able to create a magnetic field using current passing through these coils. And we saw that in the first video in the lab, right? So we could in general, we could say that, oh, well, electricity can cause a magnetic field and a magnetic field can cause electricity. But I do want us to be more specific than that. And what we can say, to kind of summarize this relationship here, is that we can say current will cause, I could be more specific, current flow through a conductor. I don't have room for that here, but current flow through a conductor will create a magnetic field. All right, that's the first part of electromagnetism. And the second part that we're going to get to next time, but not today, is that, well, the inverse of that is, well, there's something about how a magnetic field can create electricity, right? This has to do with how electricity, more specifically current, can create a magnetic field. So my claim is that the inverse is also true. Something about a magnetic field can also create something with electricity. And it turns out that what we can say, to be more specific, is that a changing, that's actually important, a changing magnetic field will cause, or will cause, this is the way I'm going to say it, will cause an induced voltage. All right, so it's not specific enough to say that magnetism causes electricity. We need to be more specific and say that a changing magnetic field in the presence of a conductor will cause an induced voltage in a conductor. All right, this is really just kind of foreshadowing for right now. All right, so this is kind of what we focused on today. Current will create a magnetic field, and we saw evidence of that, and we talked about the right-hand rule for current carrying conductors, and now you know how, by applying the right-hand rule for current carrying conductors, you know how to tell me which side is the north side, which side is the south side of the electromagnet, and we talked about how to change the strength of that electromagnet. All right, foreshadowing a little bit to next time. Next time, we're going to focus on this second part that says a changing magnetic field will cause an induced voltage in a conductor. And you can probably, reading into this a little bit, you can probably say, oh, that sounds like something that might be useful in a generator, because that's exactly what we want to do in a generator. In a generator, we want to create an induced voltage in the generator, and then we'll hook up the output of the generator to the electric grid. And that will create electricity on the electric grid. All right, so that's some foreshadowing. That's what we're going to get into in the near future. All right, but for now, I think I'm going to call that a day. And so what we've talked about today, we talked about magnetism and how it's created and some important rules for drawing magnetic fields. We talked about the units and the variables associated with magnetism and magnetic flux. And then in this video, we talked about the right-hand rule for current carrying conductors, and we talked about how to create electromagnets and how to vary the strength of the electromagnet. All right, so that's going to wrap things up for today. Once again, don't forget about the extra credit DC motor. If you have any questions about that, let me know. I'll be happy to answer them. And otherwise, have a good week, and I'll see you next time.